Hello and welcome to Data Science for Ecologists in R. In the last video, we learned how to estimate the parameters in the linear model. Today, we will follow up on this by identifying the distribution of the least squares estimates, given that the assumptions of the linear model are fulfilled. So let's start right there by quickly recapitulating these assumptions. First, there is a linear relationship between all explanatory variables and the outcome. Second, the error term is normally distributed with mean zero and variance sigma squared. And lastly, error terms for different observations are independent of each other. Let's now investigate the distribution of the least squares estimates under these assumptions by repeatedly simulating data according to a linear model. More specifically, we will consider the linear model y equals 3 plus 0.5x plus epsilon, where epsilon is normally distributed with mean 0 and variance 4. Furthermore, we will look at 20 evenly spread x values between 0.5 and 10. If we now use a statistical software to generate the corresponding y values according to this linear model, the plot might look like this. This data can then be used to calculate the least squares estimates for beta 0 and beta 1. In this case, we obtain the blue function as an estimate. We can then repeat this process as often as desired, for example 10,000 times. Each time we draw another random sample for the y values, we calculate new least squares estimates. And as you can see, there's a lot of variation in these estimates. This variation can then be visualized by looking at the distributions of the estimated beta 0 and beta 1 values, which are depicted in these two histograms. From these histograms, important properties of least squares estimates can be derived. Let's start by identifying the mean estimated values. As indicated by the red lines, we obtain a value very close to 3 for beta 0 and a value very close to 0.5 for beta 1. So the mean estimates are very close to the true parameter values. And indeed it can be shown mathematically that the least squares estimates are correct on average. This unbiasedness is the first important property. We derived it based on the three assumptions of the linear model. If these assumptions are violated, the least squares estimates might not be unbiased anymore. For example, if the true relationship between x and y is not linear, the mean estimates are not able to capture this because they define a linear function. On the other hand, we could relax these assumptions a little bit and still obtain unbiased estimates. For example, the error doesn't need to follow a normal distribution, but only needs to have a mean of 0 for all observations. In this case, the observations do not deviate systematically from the true linear relationship, which ensures that the estimates are correct on average. Let's now come to the second property. As the histograms already suggest, the least squares estimates are normally distributed. Intuitively, one could say that they inherit this property from the normally distributed errors. If in addition the errors are independent, the precise density of these normal distributions can be easily derived mathematically. The red lines show these theoretical densities, which agree very well with the distribution we also found empirically. This is the case because all three assumptions were fulfilled when the estimates were generated. If any of these assumptions had been violated, the empirical distribution would have diverged from the theoretical one. The two properties we discovered in this video can be summarized in the following way. If all three assumptions are fulfilled, then the least squares estimates follow a normal distribution with the true parameter as the mean and the variance that can be derived mathematically. It is not important to know exactly how this variance can be calculated, but you should understand that it depends on the error variance. The higher the error variance, the more variability in the estimates there is. Furthermore, it is important that it does not depend on the true values of beta 0 and beta 1. This can be illustrated by changing the true parameter values in the previous example and leaving everything else as before. For example, we could set both beta 0 and beta 1 to 0. Just as before, we can now generate y values according to this linear model and estimate the parameters. If we do this 10,000 times, we obtain the following empirical distributions for the parameter estimates. And if we compare them with the distributions from the previous example, we can see that they have exactly the same variance. Only the mean has changed because the true parameter values are now 0. Alright, now that we know how the least squares estimates are distributed, we have all tools needed to make inferences about the true parameter values. This will be covered in the next and last video of this theory block about linear models. See you soon!